Welcome to this video in which we are going to calculate the limit of this function here. So please relax, don't be scared by the apparently very complicated expression of this function. We are going to see how to simplify bit by bit all the parts of this expression. Let's start by writing this function as the numerator n of x over the denominator d of x. Now, just by looking at it, we want to understand what this limit could be. So let's look at the numerator here. The first part here, this arcsine of log. Let's start by the inner component here. 1 plus x squared goes to 1. So log of 1 is 0, arcsine of 0 is 0. So the first bit goes to 0. The second bit the same, because cosine of x goes to 1. So this guy here goes to 1, 2, and log of 1 goes to 0. And similarly here, this expression here goes to 0, 2. So the whole numerator goes to 0 as x goes to 0. So let's now switch to the denominator and see what happens. And this is very similar because the first factor here goes to 0, 2, because the arctan of 0 is 0. This guy here goes to 1, 1 plus 0, 1. And this guy here goes to 1, 2. So at the end, 0 plus 1 minus 1, the whole thing goes to 0. So we've got an expression 0 to 0, and we cannot conclude immediately. So we have to go deeply into the study of the numerator and denominator and see what happens. Now, just two side remarks. The first remark is that we are going to use, while we do this exercise, all these limits here, which for me will be known. The second thing, I'm going to use a very simple notation that will shorten the expressions that I will have to write. So we write f of x tilde, let's say, g of x, if, and this is read, f of x is asymptotic to g of x in 0. This is not precise, but we always consider 0. If the limit as x goes to 0 of f of x over g of x, if this limit is equal to 1. Okay, so now let's start. We first start by looking at the numerator n of x. So let's write it down again. So n of x is equal to, so here it is, the numerator, and we split it again into three parts. This first factor, I call it n1 of x. This second factor, I call it n2 of x. And this third factor, I call it n3 of x. So let's start by n1. So let's look now at this limit here. We have an arcsine, but I know what the sine does in 1. And so I know that sine of y is asymptotic to y. But this implies, just by applying the arcsine function, that the arcsine of y is asymptotic to y2. Okay, but then this implies that the arcsine of log of 1 plus x squared is asymptotic to log 1 plus x squared. Okay, but then, since the log of 1 plus y is asymptotic to y, and this is nothing but this limit here, then this implies that the log of 1 plus x squared is asymptotic to x squared. And finally, n1 of x, which was nothing but this expression here, this arcsine of log, this was asymptotic to the log, which is asymptotic to x squared. And so n1 of x is asymptotic to x squared. So this concludes the first part. Right, so now we have to keep going. Let's look at n2 of x. So let's write n2 of x. This is, by using the properties of the log, I can write it as 1 over 4 log of cosine of x. Now I want to isolate a 1 here, and I write the cosine as 1 plus cos x minus 1. But now I use again this formula here, and so this gives me 1 over 4 cos x minus 1. Again, we have to do a double check that here y had to go to 0 in order for this to be correct. And so here y was cos x minus 1. Does it go to 0? Yes, because in 0 the cosine is 1, so I have 1 minus 1 equals 0. So this substitution is correct. And now I have cos x minus 1. I have to go and look it up. I have another limit here. So I can replace 1 minus cos x by 1 over 2 x squared. So this is asymptotic to 1 over 4 x squared over 2. But you need to be careful, because here I had 1 minus cos x, while here I have cos x minus 1, so I buy a minus sign here. And so this is nothing but minus x squared over 8. Okay, this concludes N2. Now finally N3, this is the simplest one. N3 of x, this is asymptotic to e to the x. This is easy. E to the x in 0 is asymptotic to 1 because it converges to 1, times e to the x cubed minus 1. Well, let's look at this expression here now. E to the y minus 1 is asymptotic to y. So e to the x cubed minus 1 is asymptotic to x cubed. And this is equal to x to the power 3. Let's put all these three pieces together. We have obtained that n of x is asymptotic to x squared, here, n1, x squared. Then I have minus n2. Minus n2 gives me plus x squared over 8, plus n3 plus x cubed. And now a very simple observation is the following. You see here I have powers of 2, but here I have 3, and 3 is negligible with respect to the others, because as x goes to 0, this becomes much smaller than these two guys here. And so this is, again, asymptotic to the sum of the first two factors, which is 9 over 8 x squared. Good, so the first step is done. We have simplified very much the numerator. Just look very briefly at all the way we've gone through. We started with this expression here, rather complicated and involved, and we ended up all through all these calculations to this very, very simple expression here. So it was worth doing it. Now we just have to do the same with the denominator, and then we are done. So let's write it down. D of x was, now you remember that the limits of these three factors were 0, 1, 1. Since I like zeros more, I'm going to rewrite this as arctan of 2x squared plus square root of 1 plus x cubed minus 1 plus 1 minus e to the x squared. So this is exactly the same expression. I just regrouped it in different ways. And then I call this d1 of x. This is d2 of x. And this is d3 of x. Now we want to proceed in exactly the same way. I'm gonna go a little bit faster because the ideas are exactly the same. So again, in order to deal with the arctan, I'm going to use this limit here. So how do we do it? Let's write it down. Because the arctan seems rather complicated, it's not. Let's see how we can do this. So the sine of y is asymptotic to y. This implies that also the tangent of y, which is nothing but the sine of y over the cosine of y, this is asymptotic to y over 1, because the cosine of y is asymptotic to 1. And this is nothing but y. So the tangent of y is asymptotic to y too. By applying the arctan on both sides, we get that the arctan of y is asymptotic to y, and therefore that d1 of x is asymptotic to 2x squared, because instead of y I had 2x squared. Now let's look at d2 of x now. This is square root of 1 plus x cubed minus 1. And now we go up and look at this expression here. And we have that square root of 1 plus y minus 1 is asymptotic to y over 2. So here, this is going to be asymptotic to x cubed over 2 immediately, just by substituting x cubed with y. Okay, finally, d3 of x. This is 1 minus e to the x squared. Again, we use this formula here. E to the y minus 1 is asymptotic to y. So here I have asymptotic to minus x squared. Okay, finally, I obtain that the whole denominator is asymptotic to 2x squared plus x cubed over 2 minus x squared. So altogether, this gives me x squared, because this second factor here is negligible, is much smaller than the terms with x squared. So finally, let's see why all these efforts were actually very worth doing, because we obtain very simply that the limit as x goes to 0 of my function n of x over d of x, I can easily substitute. In the numerator, I can put this quantity here, 9 over 8 x squared, over, in the denominator, I can put this quantity here, which is x squared. And so this limit is very simply n over 8. So we saw that by simplifying all these factors in this very complicated formula here, we were able to, at the end, obtain a very simple formula for the computation of the limit, and at the end, the limit is nothing but 9 over 8. Okay, thank you for watching.